Hey everybody, I hope you're all doing well. I hope you're staying safe with everything going on right now. These are weird times. We're home, we're doing our best to figure out how to move forward with our education. What I did over the past few days is I worked on setting up this home studio. Got a TV, got a whiteboard. I'm gonna do my best to teach you as much physics as I can from this corner in my house right here. This is going to be a test video. I just want to make sure the whole system works out as it's set up. So I'm going to work out the first homework assignment I posted for assignment 1. In the future, I want to do longer videos, more instructional videos where I'll actually be teaching you new content. I'm going to work on that over this coming weekend. I'll compile a bunch of videos and hopefully you'll see more of me and less of other videos I find online. So let's get started. Question number 1 that I posted for you guys to work out. We have a positive 1.5 nanocoulomb charge and a negative 2.6 nanocoulomb charge placed 2 millimeters apart. We want to find the magnitude of the force between them, and we want to know if these charges attract or repel. Here we're going to be applying Coulomb's law like we discussed in class to figure out the electrostatic force between any two charges. So using a reference table, we know that Coulomb's law, F sub E is equal to K, Q1, Q2, all over R squared. Now we plug in what we know. The hardest thing about this whole situation is just making sure you plug in everything correctly onto your calculator. Don't forget the square, make sure you know how to use the scientific notation. So plugging in what we know, you find this electrostatic constant K in your reference table. Page 1 has all important physical constants. We know that K is 8.99 times 10 to the 9th, and that's Newton meters squared per Coulomb squared. Very important that we plug in our units. If you miss the units, it's a point off the whole problem. Next, we plug in the magnitude of the two charges we have. They gave us the charges in nanocoulombs. In order to make sure we get the correct answer, we can't plug in nanocoulombs into our equation, but if you look at the reference table, you can figure out that nanocoulombs, 1 nanocoulomb is 10 to the minus 9 normal coulombs. So we have 1.5 times 10 to the minus 9 coulombs multiplied by 2.6 nanocoulombs. It says it's negative, but we're only going to plug in positive values into our equation because we're only interested in the magnitude of the force. We're going to figure out the direction later by looking at the signs of the charges. So we can just plug in 2.6 times 10 to the minus 9 for nanocoulombs. This is all over the separation squared. Millimeters, 1 millimeter is 10 to the minus 3rd meters. So we're going to be plugging in 2 times 10 to the minus 3rd meters. Very important that we square this quantity. Plugging this into your calculator, I would use that capital E button, but just make sure that you plug in everything straight. I would do the numerator first and then divide by the denominator squared. If you work this out correctly, you should get an answer of, looking at my notes, 8.97 times 10 to the minus 3rd, and our units for force is in newtons. You can keep things in scientific notation reporting your answer. This is technically 8 millinewtons, 10 to the minus 3rd. So that's your answer for number 1. Plugging in what we know, careful calculating it out, we get a force of 8.97 times 10 to the minus 3rd newtons. That's question number 1. Question number 2. Here they give us different given information. I hope I kept that up on the board long enough for you guys to see. Okay, different given information. Now we know that sphere A and sphere B are placed 8 millimeters apart. Sphere A carries a charge of 2 nanocoulombs, and we know the force between them is 9 times 10 to the minus 6 newtons. We want to figure out the magnitude and the sign on sphere B. I realized I missed part 2 of question A. Before we do that, we want to figure out if these charges attract or repel. We have a positive charge and a negative charge, so these are going to attract. Remember, like charges repel and unlike charges attract. So those two charges are going to attract. All right, question number 2. Sphere A and sphere B. Okay, sphere A has a charge of +2 nanocoulombs. It's placed 8 millimeters away. And sphere B has a charge of unknown. We know the force between them is equal to 9 times 10 to the minus 6 newtons. 10 to the minus 6 is micronewtons. And we want to figure out the charge on B. So, again, we're going to start with our Coulomb's law equation. K, Q1, Q2, all over R squared. You can plug in and rearrange later. What I like to do is actually solve for the quantity of interest, which we'll call Q2, and then it'll be much easier to plug in and see if we can get to our answer. So I multiply both sides by R squared. Now I'm going to divide each side by KQ1. So that's going to give us R squared FE all over KQ1 is going to be equal to Q2. Now we can plug in what we know. We know that the charges are 8 millimeters apart. Again, you want to convert back to your standard SI units. We know the force between them. We know K for the reference table, and we know Q1. So the charges are placed 8 millimeters away. That's 8 times 10 to the minus 3rd meters squared times 9 times 10 to the minus 6 newtons. All over, K is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Q1 is given to be 2 nanocoulombs, 2 times 10 to the minus 9 coulombs. Working this out, you know that Q2, or the charge on sphere B, is equal to this. If you plug this into your calculator correctly, you should get an answer of 3.2 times 10 to the minus 11 coulombs. Notice here that with these kind of problems, we're dealing with really large and really small numbers. So just be very careful plugging in the scientific notation into your calculator. So that's the magnitude of the charge on B, and we want to figure out the sign. It says that sphere A carries this positive charge and it attracts sphere B. The only way for that to be the case with sphere B having a charge is this charge has to be negative. That's my strategy working these out. I usually use Coulomb's law to figure out the magnitude of the charge, and then later on we look at the question, we use our knowledge of physics to figure out the actual sign of the charge. All right, that's question number 2. Question 3. Here is a conceptual question. This is the kind of question that you guys love to do. You guys always complain about these kind of questions. We know that 2 charges attract each other with a force F. If the magnitude of one charge was doubled and the distance between the charges is doubled, how would that change the attractive force between the charges? Looking at some of your submissions, you did say that the force between the charges would decrease, and I agree with you, but I want to know exactly how much the force between the charges decreases. This is weird, teaching to a camera with nobody in the room. Anyway, so we have Coulomb's law, K, Q1, Q2, all over R squared. And we want to figure out what happens when we change the magnitude of one of the charges and the distance between the charges, how that affects the force. As you can see, the force depends linearly with the magnitude of the charges and depends on the inverse square of the distance between them. So, if we double one of the charges, and we double the distance between them. It doesn't matter what Q1 is, doesn't matter what R is, we just want to see how it's going to exactly scale the force between these two charges. We can see that this 2 gets pulled out front, but this 2 is stuck inside of the square. So this is going to be 2 squared, which is 4, and then you can pull that out front. And then we see that this coefficient here will figure out how much the charge gets scaled. 2 over 4 is 1/2. By doubling one of the charges and doubling the distance, you see that we'll cut the force exactly in half. You can plug in any numbers no matter what charge you have, what distances you have away. By doubling one of the charges and doubling the distance, you will always half the force between those two charges. And that's it. I hope you enjoyed this video. I'll be putting together a lot more videos in the future. I guess we're good. All right, guys. I'll see you soon.